part 2. I literally typed in the exact same thing, but I typed it in on my computer instead of up here, and now it should actually work. So again, I have that d dx of y1. If we go to the graph, you can see here in red, that is the equation of the derivative. Now, the equation itself may look familiar to you, and we're going to actually look at some of the table of values. So second graph, we're going to look at the table. Notice 0, -1, -2, those all give us errors. But we have 1, 1, 2.5, 3.3333, 4.25, 5.2. So I'm going to type some of the, or write some of those down over here so we can take a look at those. So 1 was 1, 2 was 0.5, 3 was 0.3 repeating, 4 was 0.25, 5 was 0.2, and I don't know if you guys see some kind of pattern here. 0.5 as a fraction is 1/2. 0.3 repeating as a fraction is 1/3. 0.25 is a fourth. 0.2 is a fifth. So the derivative function is 1 over x. And this is something that we will actually prove in a later section, so you don't need to worry about that right now. However, there is one catch. You can't just say that the derivative is 1 over x and leave it at that, because you need to think about the domain. The domain of this original natural log function is 0 to infinity. You can't actually take the natural log of 0, that does not exist, but the very next number after 0 you can use, and it goes the whole way up to infinity, which means the domain of your derivative cannot be larger than the domain of your original function. So since 0 to infinity was the domain of the original, 0 to infinity has to be the domain, at least the domain of the derivative. Now the derivative does not exist at 0, but that doesn't matter because 0, again, was not part of the original domain. So you can exclude domain numbers going from the original to the derivative, but you cannot add numbers back in. Just something to keep in mind here. And I know I didn't actually sketch this graph out here, but it would basically look something like this. And you can see that is the 1 over x. Typically, though, you have this other piece. But again, that other piece doesn't apply because it's not part of the original domain. Okay, which brings us to theorem 1. Differentiability implies continuity. And this is something that I was talking about a little bit earlier. If f has a derivative at x equals a, then f is continuous at x equals a. All things that have derivatives are going to be continuous. So if you know there's some point a where there is a derivative, then it has to be continuous at that point. It is important to note the converse is not true. Just because something is continuous does not mean that it has a derivative. Think about the absolute value function. That's the perfect example of this. An absolute value function is continuous. However, there is no derivative of an absolute value function at its vertex, so it does not fit. So if something it has a derivative at x equals whatever value, then it is continuous at that same point. Keeping along with that, now we have theorem 2. Theorem 2, the intermediate value theorem for derivatives. So if you have a and b are any 2 points in an interval on which f is differentiable, then it has to take on every value between f prime of a and f prime of b. So this is going along with the intermediate value theorem that wasn't for derivatives, that just said if we knew a function was continuous, then it had to take on everything between a and b. So this is saying if you have the slope at a and you have the slope at b, and we know it's differentiable from a to b, then every derivative would have to exist. For example, if f prime of a was 1/2 and f prime of b was 7, there has to be, from a to b, if it's differentiable, there has to be some point between a and b where the derivative is equal to 5. There has to be some point between a and b where the derivative is equal to 4.3. There has to be some point between a and b where the derivative is equal to 6.7. So everything between those has to exist. So here, does any function have the unit step function as its derivative? That would be, for all negative numbers, that would be -1. For all positive numbers, including 0, that would be a +1. This is the unit step function. And the answer to that is no, because if you have some a value that's less than 0, you're going to get back -1. If you have some value that's greater than 0, you're going to get back +1. There is no way to get anything in between -1 and +1, which means it does not fit the intermediate value theorem, so it can't be differentiable, because that differentiability has to exist. And then a very important statement down here. The question of when a function is a derivative of some functions is one of the central questions in all calculus. So this is one of the big ideas. This is one of the main reasons why calculus exists. Okay, lastly, we have your homework. Now, obviously, this is not due Thursday, as I told you guys earlier. And as posted in Schoology, this assignment is due on Monday, but these are the correct questions. Please look back over this in the previous video, because we had some minor graphing technical difficulties. But just like with everything else, look over this, watch the book video as well, because it has a lot of great information in it, and contact me if you have any questions.